Alright, in section 6.1 we're going to talk about slope fields, and today mostly we're just going to be talking about differential equations and proving that something is in fact a solution of those differential equations. We'll get in more to the slope fields later. So on this particular problem, this is asked us to verify the solution of the differential equation. So what I'm going to do is, first of all, I need to find what y prime is so I can plug that back in to see if it's a true statement. So y prime is actually equal to, we know the derivative of e to the negative 2x to be e to the negative 2x times the negative 2. So I'm going to put the negative 2 out front. Over here, I'm going to show that this is actually the solution. So I have 3 times negative 2 e to the negative 2x, and again all I'm doing is making substitutions in here, and then I have plus 5y equals negative e to the negative 2x. Now I can't really solve any types of equations here because I have a y in here, so I need to go back and get what y is equal to. So I'm going to go ahead and simplify this at the same time. I've got negative 6 e to the negative 2x plus 5 times e to the negative 2x. And really we're asking ourselves, does it equal negative e to the negative 2x? Well, if you look here, negative 6 and a 5 does give us a negative 1 e to the negative 2x. And since those two are equal, I have verified that the solution of the differential equation. This next problem, again, that's what we're doing. We're verifying the solution of the differential equation. In order to do that, I need to have what dy over dx is equal to. So I'm going to go ahead and find dy over dx here. So I'm taking the derivative with respect to x, so I need to put 2y, and then I need to add in my dy over dx, minus, I've got a 2, and then ln of y would be 1 over y dy over dx is equal to negative 2x. Or sorry, I said negative 2x, I just meant 2x. Looking on this side, I can take out a dy over dx on both of those terms, so I'll do so. That gives me 2y minus 2 over y, and that equals 2x. And then what I'll do is I'll divide. So I get 2x over 2y minus 2 over y. Now these don't look the same. So what I'm going to have to do is start to simplify by making common denominators. I need to do that because there's no fractions over here. So 2x over, I'm going to have to make y be my common denominator. The second fraction doesn't change at all, but the first fraction would become 2y squared. So now what I have when I combine like terms is I have 2x over 2y squared minus 2 over y. Now what I need to do is get a little bit more space here. So I've got dy over dx is equal to 2x over 1 times, do the reciprocal here, y over 2y squared minus 2. Really, the only thing else I can do is factor out my 2 down on bottom. And now if I look, I can cancel those, and I get xy over y squared minus 1. That is exactly what this is equal to, so I verified the solution. Alright, in this problem, the question slightly changed. It now says determine whether the function is a solution of the differential equation. So this one right here, this part, actually refers to the fourth derivative. So let's go ahead and start to work with that. Well, if I'm going to find the fourth derivative, I'm going to need to find the first derivative first. So y prime is equal to 2 cosine x. And I'm going to go ahead and write that problem over here. The fourth derivative minus 16y is equal to 0. Trying to verify or determine whether the function is a solution. We have the second derivative, which would be negative 2 sine x. The third derivative would be negative 2 cosine x. And then the fourth derivative would be taking the derivative of cosine would make a negative sign, so we'd actually end up with a positive 2 sine x. So I end up right back to where I started. So I'm going to go ahead and plug in 2 sine x minus 16 times, well, what's y equal to? It's this part right here, 2 sine x. And does this equal 0? No, definitely doesn't equal 0, so it's not a solution. On the next problem, we're doing the same thing. We're going to determine whether the following function is a solution to the fourth derivative minus 16y. So when I find the first derivative here, I have 3 cosine of 2x times 2. So that actually makes my first derivative read 6 cosine of 2x. My second derivative would be the derivative of cosine, which is negative sine 2x times 2, which would be a negative 12 sine of 2x. My third derivative would be negative 12 cosine of 2x times 2. So that gives me a negative 24 cosine of 2x. And then my fourth derivative would be negative 24 times negative sine of 2x times 2, which gives me 48 sine of 2x. So when I plug that back in up here, the fourth derivative, 48 sine of 2x, minus 16, and then what is y? Y is this, 3 sine of 2x. Does that equal 0? Well, this does give me 48 sine of 2x, and it is the minus in front of there, so I do end up getting 0 for my answer. So yes, this is a solution. The last problem for this video, it says determine whether the function is a solution of the differential equation. So again, I'm going to need to find the derivative. The derivative happens to be a product rule, first times derivative second, plus the second times the derivative first. That will rewrite into x squared e to the x plus, I have to distribute, so I get 4x plus 2x e to the x. What I have here is I have x, y prime minus 2y equals x cubed e to the x. So I'll plug in my y prime as x squared e to the x plus 4x plus 2x e to the x. And I'm just copying that down. Minus 2y, well, the y is x squared times 2 e to the x. And then does that equal x cubed e to the x? Well, if I distribute this out, I get x cubed e to the x plus 4x squared plus 2x squared e to the x minus 2x squared. That would be a 4x squared when you multiply that all together. And then I have a 2x squared, a negative 2x squared e to the x. And then I have that equals this part here. I'm not going to finish, but it is a solution.